Good afternoon. Okay. Section 11.7. Strategies for testing series. Okay, so today is a very important lecture because in a sense it summarizes the many things that we have learned about series and how to test for convergence. We'll go through a bunch of examples and show, when to apply which test. But first I'll give you a list of tests, right? And list of facts which you should remember to study convergence of series. So let's give a list first. So first let's look at a series like this. Okay, you should all remember. Do you guys have questions there? Questions? Okay, she has a question. Okay, so this is called the P series. And it converges if P is greater than 1 and diverges if P is less or equal than 1. Okay, so this is something that we have to remember. We're going to compare a bunch of other series to this one. Another one, a standard one, is, as I told you before, this is the geometric series. And it converges if the absolute value of R is less than 1 and diverges if the absolute value of R is greater or equal than 1. Okay. These two are your staple series that you should know everything about. Okay, so now tests. What kind of tests have we looked at? We have comparison tests. This is when we have a series that we know something about and a series that we doesn't know, where we don't know anything about. And by comparing the two, we can conclude about the unknown one. Okay? So there are two types of these tests. So one is, to formulate these, we say that there are two series, AN and BN are positive. Okay. So if AN is smaller or equal than BN and BN converges, then AN converges. On the other hand, if AN is greater than BN, then if BN diverges, then AN also diverges. Okay? So this is a test which requires us to compare them term by term and prove that this holds for every n starting from a certain finite number, not necessarily from 1. Okay? Or we have another version of this test, okay, which requires us to evaluate the limit. So if we look at the limit as n goes to infinity of the ratio between the terms, and we say that this is a constant C positive and not finite, okay, then the behavior of the two series is similar. They either both diverge or they both converge. Both converge or both diverge. Okay. So again, there are two variants of the comparison test. One requires a term by term comparison. The other one is a limiting version of the same thing. Fine. Number 4 is a test for divergence. This is the easiest one. Test for divergence. So if the terms don't go to 0, okay, then the series for sure diverges. If they go to 0, then we don't know. Okay, but if they don't go to 0, then for sure we can stop. Let's say it diverges. Number 5, alternating series test. So the series should have this form or something like this, okay, n minus 1 pn, something like this. Alternating series test. So do you remember what we have to test? So if bn plus 1 is smaller or equal to the previous one, and the limit of bn is 0, then converges. Then an converges. Okay. So if we have this alternating sign, we have the special test for such things. Good. The ratio test. There are 3 more tests. Okay, so I go here. Six is the ratio test. So here we're looking for the limit as n goes to infinity of the next divided by the previous absolute value. So let's suppose it's equal to L. Depending on L, we have convergence, divergence, or we don't know. So if L is less than 1, it converges. Greater than 1, diverges. L equals to 1, the test is inconclusive. And so when do we apply this? So here we can say that if we have products or factorials, so if these things are contained in the definition of an, each term, then you see what happens when we divide the next one by the previous one, we get a lot of cancellations. So when we use this test, this expression simplifies, and we can easily, investigate the convergence of this thing. So products and factorials. Now, a similar test is the root test. So this is when we have when an is something like bn to the power of n. When each term is something raised into a power n, then this is a really good test. So we look at the limit of nth root of an, okay? And we call it L, and we have the same conditions, just like here. So I'm not going to repeat them. The last thing is called the integral test. This is when we can use our knowledge about the improper integrals. So let's suppose that an is a function that like a factorial would not do here. If I have a factorial, I don't really have a function that corresponds to that, at least not in this class. So let's suppose that I can express an as this function, and f is continuous, positive and decreasing, and decreasing. So 3 things that I have to check for the function f. Most of them are continuous, and these 2 are usually easy to test. So then the series converges if and only if the integral of the function converges. So what is if and only if? What does it mean? If this guy converges, this guy converges. If this guy diverges, this guy diverges. Okay? So they have the same behavior. By looking at the integral, I can find out the convergence properties of the series. The answer, the sum, is not going to be the same. It's not given by the integral, not necessarily. Okay? So this is the summary of everything. And for the rest of the class, I'm going to give you examples, lots of examples. Okay. So the first example is the easiest. So let's suppose that we have n minus 1 to n plus 1. If we look at individual terms, as n increases, okay, we can see that they don't actually decay to 0. If we look at the limit of an, so n minus 1 to n plus 1. So I know just by looking at it that it doesn't go to 0. How do I know? Well, that giveaway is that the highest power of the numerator is the same as the highest power of the denominator. Okay, this is something that you probably know already. Could you guys stop talking? I cannot take this anymore. The 3 of you. I'm going to ask you to leave. Okay? Thank you. So I'm looking at the power of numerator and denominator. If they're the same, then the limit is going to be a constant, which is not 0. If the denominator has a higher power, then it's going to be eventually bigger than this, and the thing goes to 0. If this power is greater, then it's going to infinity. So this is how you can tell just by looking at it. If you want to go through the steps, you divide by the highest power. Okay. So here we divide by n. These things go to 0, and that's a non-zero constant as predicted. Okay. And this means that the test for divergence tells you that the whole thing diverges. I'm going to say an diverges. Okay. The least requirement that we have for convergence is that these things go to 0. Was there a question here?
Isn't it 1/2 is less than 1?
It's less than 1 for sure, but it's not 0. So imagine adding up an infinite number of numbers. So if they don't eventually become 0, you keep adding a positive number together, right? And the sum is going to diverge. So for the test of divergence, this limit has to be 0. Okay? If it's non-zero, then for sure we have a divergence of the whole series. Was there a question?
If the equation was n plus 1 over 2n plus 1,
n plus 1 over 2n plus 1.
would the integral test work there?
Would the integral test what?
Yeah. Can we use the integral test in that one?
In this case, I would still use the same test for divergence. Because if I look at the limit of this guy, again, it's 1/2 not equal to 0 diverges. And my advice to you is that whenever you can use this test, whenever you can show that these numbers don't go to 0, don't use any other test. Just check that first. If you see that these things don't go to 0 as n goes to infinity, then for sure the series will diverge. Okay. More questions? Question?
Slight one. For the integral test, it's written that if f is continuous, positive, and decreasing,
Yes.
then the two behaviors are identical in terms of convergence or divergence.
Right.
I'm wondering, is that condition said because if f is not positive, or if f is not decreasing, then there's no point the series would diverge anyway? Or is it that only in those circumstances do the two behaviors?
Yeah, if f is not decreasing, then an is not decreasing,
Right.
And the divergent test would be satisfied, and it will diverge.
Okay.
Yeah. So this holds when we don't use that test. We can use this test.
But if we were to use that test, it would still work, but this is just radically easier.
Right.
Okay.
You're right. Mm-hmm. Okay. Now, actually, no. I'm sorry. I gave you a wrong answer. So I just found a counterexample. So let's suppose that my function f of n is going to be equal to sine pi n times n squared. Okay? Squared. Okay. This function looks like this. It's not decreasing, and it for sure diverges when I try to integrate that. Now, if I only restrict myself to integer n's, I can see that all the terms of my sequence are 0. Okay, so we can only use this test under these circumstances. Otherwise, it can be misleading. Okay, thank you. That was a good question. I caught myself. Okay. Okay. Next. Let's look at this. So this is 3n cubed, 4n squared, plus 2. Okay. So you can see that this belongs to a large class of examples where we have algebraic functions. Okay, algebraic functions, and these guys are usually compared to P series algebraic function. So I have to find the P series that's most closely related to this. How do I do this? There's one algorithm that you can always use. Okay, so let's look at AN. So AN is my general term. N cubed plus 1, 3n cubed plus 4n squared plus 2. How do I find Bn? That is a P series that looks like this. So what I do, I'm going to leave only the highest power of the numerator and the denominator. So I'm going to look at cube root of n cubed times 3 n cubed. Okay? And I ignore the rest. Okay? Now I simplify it. N 3/2, 3 n cubed. What is this? 1 over 3 n 3/2. Okay, this is my guy. Okay, so it's always going to work like this. So whenever I have any radical on top or at the bottom, any polynomial, stuff like this. So I look for the highest power and get an easy expression that by definition is going to look like a p-series. Okay, so Bn is this. Now we know that we have to compare the two. Which comparison test do we use? One compares them term by term. And it's horrible to compare this with this, right? We have to prove that one is always greater or smaller than the other one. So in these cases, it's always better to use the limiting test. So we are going to look at the limit of an over bn. It's a lot easier, and usually it works better. So we write down the whole thing. 3n cubed plus 4n squared plus 2. This is an. Bn is this, so I have 3n 3/2. So I have to take the limit. Before I take the limit, I'm going to simplify it by bringing this guy under the square root. Okay. So when this makes its way into the square root, it gets squared. So I have 9n cubed, multiplying each term under the square root. So I have 9n 6 plus 9n cubed, okay? And I have 3, sorry, this is the limit as n goes to infinity of this. Okay, so now it looks decent, and I can, for instance, divide everything by n cubed, right? So I have 9 plus 9n minus 3, and I have 3 plus 4n minus 9 plus 2n minus 3. So to do this, I have to be very comfortable with manipulating square roots. Whenever I want to multiply and divide anything under square root, it gets squared. If it's a cube root, it gets cubed, and so on. Right? Okay, now it's easy because everything that contains n to the negative power goes to 0, and I have 3 over 3 is 1. So what is the test? We want to see that the two sequences behave similar. So the limit has to be non-zero and not infinity. And that's what I have. Okay, it doesn't have to be less than 1 or anything like this. They just have to differ by a constant. Question?
I was going to say, so since you got a finite answer for the limit, you know that they both converge and diverge.
Yes.
Then would you just look at what the p-series rule is?
That's the next step. So I now know that they behave in the same way. Let's look at the p-series. I could have done it to start with, right? So this is a p-series with p equals 3/2 is greater than 1. So this converges. So an also converges. Okay. Very good. Questions? Okay. Okay, so the next example involves an exponential. Okay, so I'm going to do this by two different methods, okay, and either of them will work. So first of all, you can see that an can be expressed as a function of n, which is this. So now we'll look at f of x, where you write it in terms of a continuous variable of x. this guy involves a negative exponent. So you can prove that it actually decays. Okay, so it's greater than 0 for x greater than 0, and it decreases. And it's continuous, right? So this function is good to use for the integral test. That's the last test that we looked at. So as long as the integral converges, my series will also converge, and the other way around. So we have to look at the integral of f of x dx. And the reason we want to use this test is because we know how to integrate this guy, right? It's what is the method here? Substitution, right? So we consider 1 to t x e to the minus x dx. U squared is, if you like, minus x squared. Du is minus 2x dx. And when x is equal to 1, u is equal to minus 1, x equals to t, u is minus t squared. So minus 1 minus t squared, 1/2 e to the u du. Okay. Let's flip it over. Minus t squared to minus 1 e to the minus to the u du. So I have okay. Fine. So I did the integral for t. Now the integral from 0 to from 1 to infinity, x minus x squared dx is the limit as t goes to infinity. So what's the limit? We have t goes to infinity. This is a negative exponent, goes to 0. I get e to the minus 1 over 2. So converges, right? Therefore, an also converges. Okay. So this is a method that works here. Questions about this one? If you don't want to use the integral test here, there is another method to use, which is the ratio test. Okay, let's do it there. It is often the case that you can use more than one method to study the same example. Right? We can also use the ratio test. So we have to look at, let's look at an plus 1 over an. Okay, so n plus 1 e to the minus n plus 1 squared. That's a1 n plus 1. We divide that by n e to the minus n squared. Okay, and so let's simplify it a little bit. N plus 1 over n. And I'm going to bring this over with a plus sign and expand this expression. Minus n squared minus 2n minus 1 plus n squared from the denominator. So I'm manipulating the exponents. And these two guys cancel. So I have n plus 1 over n e to the minus 2n minus 1. So I'm doing the limiting ratio test. I want to take the limit of this guy and to show that it goes to 0. I'm sorry, that it goes to something that's less than 1. So n plus 1 over n e to the minus 2n minus 1. So how do I deal with this? You see, it combines a fraction like this with an exponent. So I'm going to divide both things by n. So I have 1 plus 1 over n divided by 1 from here. And this I leave as it is. Okay? So this is the limit. I can take this limit. And of course, we have a negative exponent here, which gives me 0. Okay. This is not a case of L'Hopital's rule or anything like this. But I don't even need 0. All I need is a constant that is, less than 1. So I'm fine here. So we can say that the series converges. Questions? Okay. Very good. So what's next? So the next example contains minus 1 to the n. So what can we say about this? You can see that this is an alternating series. And this is, of course, an obvious candidate to apply the test that has the same name. So use alternating series test. Okay, so what does this test require? It requires us two things. Bn less or equal to Bn plus 1. No, the other way. That will be growing. I want them to decay. And I want the limit of Bn to be 0. Okay? So, what's Bn plus 1? N plus 1 cubed divided by n plus 1 to the 4th plus 1. So I want to know whether it's less or equal than n cubed n to the 4th plus 1. So this is a little bit difficult to argue just by comparing the terms. What I'm going to do instead, I'm going to look at the function, okay, which is just this, and see if I can prove that the derivative is negative, then that does the job. Okay. So in general, you can either look at the terms just as they are, and by some simple reasoning say, okay, this is obviously, I'm adding something in the denominator, so it makes it less. If you can't do that, look at the function if you can. Okay, and then by evaluating the derivative, we can say a lot about the behavior. So I'm going to look at the derivative with respect to x. So 3x squared x4 plus 1 it's a little bit messy, but it's nothing. So sorry, let me just write down f of x here for you. It's x cubed x to the 4th plus 1. So this is the one that I'm differentiating. It's a fraction. Differentiating a fraction is relatively easy. I just have to simplify. And all we need is the sign of this guy, right? So the denominator is always going to be positive, so I don't have to worry about it. I just have to manipulate the numerator. And I'm going here to this blackboard. So collecting the terms this is the final simplification. Okay. So this is a simple expression, and its sign depends on the sign of 3 minus x to the 4th. Obviously, when x is equal to 1, this is positive. But starting from 2, you can see that x to the power of 4 is much larger than 3. Okay? So for x starting from 2, and I don't care about 1.5. I'm only worried about the integer numbers. So for if it's greater or equal than 2, f prime of x is negative. So we can be assured that the terms of the sequence decay. Right. Questions? So to show that each consecutive term is smaller and smaller, I looked at the function, I took the derivative, it's a decaying function, so the terms decay too. Okay. Now, what was the second condition? The limit, right? I have to show that the limit, as n goes to infinity, of Bn is 0. So what's Bn? It's n cubed and 4th plus 1. So again, can I do it without any further calculations? So what do I have to do? I have to look at the power of numerator, power of denominator. This is greater, so the limit is 0. If they were the same, the limit would be a constant, which is non-zero. If this was greater, then I would have infinity. So I'm just going to say 0. Okay, questions? So conditions 1 and 2 are satisfied, and an converges by the alternating series test. Okay. Question?
If the power is a fraction, can we still use that?
Yeah. Even if they're fractions. More questions?
If the limit is not 0, you cannot use this test, right?
Say again?
If the limit is not
No. If the limit is not 0, then it fails. Okay. Next example. So 2 to the n factorial. So this test calls for this series calls for the ratio test because it involves a factorial. So it's a good candidate for the ratio test. So we have to look at an plus 1 over an with absolute values. Everything is positive, so I'm going to get rid of the absolute values. 2n plus 1, n plus 1 factorial divided by 2 to the n factorial. You have to remember what the factorial means. So first I cancel out 2 to the n. I get 2, and here I have n plus 1. Okay. Questions? Now I have to take the limit. an plus 1, an. What do I have to require? I have to require that the limit is a constant less than 1. Okay? That's all I need here. And it's 0, obviously less than 1. So an converges by the limit ratio test. Question?
So how did you get that equals 2 over n?
Yes. So let's write it down here. So I have 2 to the n by 2 is this, times n factorial. And this n plus 1 factorial is nothing but n factorial times the next one, x plus 1. And this to the n. So to get n plus 1 factorial from n factorial, I simply have to multiply n factorial by the next number, n plus 1. Right? So this cancels, and we get this. More questions? Okay. The next example involves something that resembles a geometric series. Okay? You can see that if I get rid of the number 2, this is the geometric series. So compare with the geometric series Bn equals 1 over 3 to the n. Okay? So I don't want to worry about a term-by-term comparison, even though I could do it here. I always prefer taking the limit. So I have an over bn. Okay. So I have 2 plus 3 to the n, and I have 3 to the n. I can, for instance, divide the whole thing by 3 to the n. 2 times 3 minus n, or rather 2 over 3 to the n plus 1. And the limit is 1, okay? And is not equal to 0 and is less than infinity. That's all I need. It means that the two series behave similarly in the context of convergence. So how about this one, this geometric series? This geometric series has r equals what? What's the value of r here? By how much do terms differ from each other? 1/3 less than 1, right? So it converges. So the whole thing, an, converges. Okay. Questions? Fine. I have many more examples here. We can continue when we prepare for the final, but I'll start doing some of them. So we can look at the following. N to the 4th plus 1, n to the 5th plus 1. Okay. You can see that there are two polynomials. I'm going to use a comparison test and compare it with a p-series. How do we make a p-series out of it? So Bn. Remember, I'm keeping the highest power of numerator and denominator to make Bn. So it's n to the 4 divided by n to the 5. That gives me 1 over n with p equals 1, right? So this guy diverges. Now, comparison, I can just take the limit of an over bn, limit of n to the 4 plus 1, n to the 5 plus 1, divided by 1 over n. So I multiply by n here. Let me multiply through by the first power of n to the 5 plus n to the 5 plus 1. What's the answer without doing any more calculations? It's 1. It's the coefficient in front of this divided by the coefficient in front of this, 1. So it's not 0, it's not infinity. The two behave the same. This one diverges, then an diverges too. Questions? Okay. Minus 1, n minus 1, cube root of n minus 7. Some ugly formula. Okay. So I want to use the alternating series test for this one. Yeah. Use alternating series test. So we have to look at Bn plus 1 and show that it's less than Bn. This is as you can see, this involves a function which looks like this. So all I need to do is to calculate the derivative of this. I'm going to rewrite this as a function of continuous variable and use the tools of continuous analysis to help me reason about the behavior of this function. So f prime is given by cube root of x minus 7 squared times 1/3 x to minus 2/3. Okay, you can see that this is a square, this is the power of x, and I have a minus sign. So the function decays or decreases. Therefore, Bn plus 1 is going to be smaller than Bn. The second condition is the limit as n goes to infinity. You can see that this power, this is going to be to increase indefinitely, so the limit is 0. So I have a check mark here too. So the series converges. Okay. Well, I want to also show you. Give me 2 more minutes. Yes.
With that example, why can't you compare n to the 4th and n to the 5th?
Compare.
Yeah, because like since n to the 5th is larger than n to the 4th, wouldn't it convert?
Oh, I have an n here. I have an n here, so I have to bring it together like this. Right, so I have to have a polynomial in the numerator and a polynomial in the denominator. So so over here I have a polynomial times another polynomial. So I have to multiply through, and this way I have a ratio of 2 polynomials. Only now can I compare the powers. Otherwise, if I think that the power is 4 now, I'm missing this whole power of n, right? It gives me an additional power of n. Question?
For that part where you say n to the 3 halves,
Uh-huh.
should it be n to the 1/3?
Yes. Thank you. Thank you. Yeah. More questions? Question?
How did you get for the f prime the 1/3 x to the negative 2/3?
So I need to calculate the derivative of x 1/3. d dx is 1/3 x to the minus 2/3, right? So I can use the chain rule. First I differentiate 1 over something. So I get the square here. And then I have to differentiate this whole thing with respect to x. And by this formula, I get this multiplier. Okay. More questions? OK, thank you.